introduction stated, I was doing a lot of character animation. Pretty much my entire career was in computer graphics. So the question that we always ask ourselves is, how can we make our character animation realistic? But recently, we've been asking a different question, and I thought it was super exciting. How can we make our character animation real? And I think this is exciting not just for computer graphics, but also robotics, because it feels like things are starting to get closer to each other. And a lot of things we learn in character animation from computer graphics world is very, very relevant to what we're doing with robotics today. So humanoids, that's the topic of this workshop. So we're seeing all different kind of humanoids, right? There are humanoids that can observe the world, they can manipulate objects in the scene, but they don't move too much. They don't move around too much. But we're also seeing humanoids that can move everywhere, roaming on Earth, but they are mostly blind. And recently, we start to see, humanoids that can do both. It can manipulate. It can also, move around a little bit in a relatively controlled setting. Indeed, that's what everybody's trying to do. We want to be able to have combine navigation, manipulation, and locomotion, 3 fundamental skills into this one humanoid embodiment. And before we go a little bit further, before we go any further, I want to first kind of, just make sure we're on the same page. When I talk about humanoids, I mean a bipedal robot with egocentric vision, perception, and also dexterous hands. I know this could be controversial, but hopefully we don't need to spend too much time arguing about it. The reason I just feel like we are really at the moment that this is happening, there's very soon we will be in a situation where there's no reason to use wheels or grippers anymore because we solve all the problems because of you guys and everyone else. But the question is still, how do we create a humanoid policy that can do all 3 fundamental skills from basically mapping the observation of the world to this really complex action space that includes the full whole body manipulation, dexterous hands, and condition on this open vocabulary language. And that is still very difficult and challenging research direction. And I guess the first question that came to mind is, do we even have the data for us to train a policy like that? And if you're talking about in-domain data, like teleoperation data of a humanoids, I think right now the answer is no. We don't have a lot of that kind of data. People are collecting them, and that's why we build those teleoperation systems. But we do have a lot of really realistic, or actually the 3D human motion data captured from the real world, so the real human data from motion captures. They give you a lot of this detailed joint angles, kinematics data. And the problem with that is that they're not directly usable, and that's kind of the topic I want to cover today. How do we make it usable? And in addition to that, we have the entire field of computer animation, which is really good at synthesizing infinite amount of data in different scenarios from the real world motion capture data. But the problem is still they're not usable, just like real world mocap. In addition to that, just by definition, the synthetic data is not going to be as fidelity, it has the same level of fidelity as real data. And finally, we have another source of the data, which is a video human motion data. But it's also something that we had to work hard to get it into 3D, perhaps, to be usable. Okay, so today I just want to focus on my current belief is that we have enough of a real human data, mocap data, plus the data we can synthesize to actually train a very good base foundation humanoid policy. And then once we have that, we can start collecting a lot of in-domain robot data and also possibly the egocentric video data. And then that's, so I see the first step is to actually utilize the best real human data or synthesized 3D human data we have to get a good foundation for humanoid policy. Okay, so how do we go from motion capture data to robot policy? And I see there are many gaps, and I'm pretty sure previous talks have been covered a lot of them. The first gap is the embodiment gap, right? It doesn't matter how close our humanoids look like humans. There's just a lot of kinematics, dynamics, differences that we have to overcome. there's a state to action gap, because if you look at the human motion capture data, it's really just the kinematics, joint angles. What we really want is the action, or we want both, right? We want to be able to extract the joint torques or whatever action space that you define from this kinematic information. And then there is the egocentric vision gap, right? Because the biggest difference, you asked me, between character animation or computer graphics and robotics, I would say is computer vision. We don't care about perception in graphics, but in robotics, that's, you have to actually, reason about the world based on your onboard sensors. You can just assume that everything, all the privileged information is readily available. And finally, there's the scene to real gap. Okay, so I'm gonna talk all about all the gaps that leads from motion capture data to humanoid policy today, but in a relatively rapid pace. All right, so let's start with the embodiment gap. This is just retargeting problem. If you ask any computer graphics person, given a motion, that source motion, you want to display that on a target, a target skeleton or target model. And computer graphics has developed a very sophisticated algorithm that can handle really complex motion and interaction between multiple agents. But I don't think we need any of that for robotics. Let's just see if we can just retarget a relatively reasonable motion to a specific robot that almost looks like human. So the simplest possible algorithm would just work, right? Let's just copy joint angles directly on robots. But of course, very quickly you see that anything about the Cartesian space, the constraints in the XY space will break immediately if you just copy paste joint angles. Then the next best thing everybody knows in this room we know is just IK, right? We're using inverse kinematics. But we can't really just do IK immediately because robot comes in all different sizes. Like most of the human motion relatively plus minus maybe 20% of my size. But robot can be very big or very small. So we had to scale them first. And currently this is what most people would be doing. They take a human motion, human skeleton, where the source motion is from, and then they scale down to fit their robots. They scale the bones of the skeleton, and then they extract those Cartesian constraints from the motion, and then they do IK. But if you try to do something like that, you immediately make a mistake, right? Because as soon as you scale the bones, all those invariants in the Cartesian space is not preserved anymore. And if you just directly get that constraints, they're not going to work, right? The IK is just going to, you're going to force the motion to a constraint that doesn't have that invariance anymore. So the idea is really just not scaling the bone. You should directly just take you should transform the constraint in such a way that the invariance is preserved. Okay, so that's just one small point. Another thing is that there are so many things you could do just during the retargeting process. So for example, balanced, right? This is something that we kind of know how to preserve. Like you look at the center of mass in terms of the frames of your support. And then if you try to, this is one illustration here. We look at the motion we retargeted, it looks great. But if you try to look at the projected center of mass in the frame of the feed, you can see that the human motion and robot motion, they're completely different. And turn out that we need to retarget our G1 slightly different to incorporate balance. You can see that the G1 has to slightly limp backwards in order to make sure that the center of mass matches the center of mass of a human. And with that balance-aware retargeting, we're able to retarget a large-scale data set from AMAS, human mocap data set. So now we have somewhat reasonable retargeted human motion. What can we do with it? So we can start looking at the next gap, state to action gap. So one thing to overcome this gap is just to use RL, right? Because basically you can train RL to track a kinematic motion, and then you can get the action out of it, and then the action will work at least in the physics simulator. But if you take it one step further, which previous talks were already covered some of them, if you want to really use this RL policy for teleoperation, for something that you can later on, collect the data to train the robots, then the requirements for this RL policy is a lot higher. You can't just do deep mimic or some kind of single trajectory tracking. So because the demonstrator will do basically give you any arbitrary trajectory in real time, you need to be able to track that. And we use a very similar techniques that previous paper also mentioned. You can train a teacher policy, a teacher student policy. You can use a teacher policy strategy to train your policy. And the interesting thing about this the teacher policy, the privilege information, what is the most useful privilege information we can have? And in our previous work, we found that the future information usually is. And this is something that computer graphics people also figure out a long time ago. Like if you just give you the future trajectory to your character, your agent, the motion can look a lot better. And then they have another model try to figure out how do you predict future trajectory. But anyways, in this case, this is privileged information. We can use that. But once we apply to the students, you need to actually remember how the teacher behaves. So through this behavior cloning process. And with that, we're able to, during the inference time, we can replace the data set with a real-time live stream of human motion captures through our retargeting procedure, and then drive this student policy, which in turn drives the G1 robot. Okay, so let me just show a few demos that we have. So this is a fully teleoperated robot right now. And you can see that because a human has a full body as an interface, you can do not just carrying at the same time. You can also use your foot, use a different part of the bodies to be truly whole body manipulatable. And here in this example, we show that the range of motion can also be tested. Bending down, picking up things. And the really important part of this teleoperation system is we want this policy to be able to handle balance, low-level balance on its own, so that the demonstrator will never need to worry about balance. And another interesting thing that we could do is to make robot to do something more multitasking, open the door, carrying things, getting out of the door, go shopping. Okay. So this is where we show that the demos you can actually have a we show the demonstrators behind the scene, and then the robot's pretty responsive. Okay, all right. So that's a teleoperation system that we could achieve today with just a pure motion capture data. But that's not what we really want. What we really want is to have autonomous robot that could actually come up with those motion, right? Not being puppeteered all the time. So we need to have an automatic human motion generator conditioned on some high-level user commands. And one thing to do that is that you can train a generator, could be a diffusion model, diffusion policy, that can output kinematic poses in real time, and then you have this RL policy to track. And we did very similar things so far as only in simulation. So here we have this agent that is capable of following high-level, human-level instructions. So here the user say, I want to do yoga in front of the TV, and this is how the room looks like. And with this LLM, of course, VLM support, the agent can come up with the plans and figuring out, okay, in order to do yoga, I need a clear space, I need to move the trash can and this floor lamp out of the way, so that I have a space to do yoga. So that's really just something that everybody can do with a VLM nowadays, right? Because all those high-level planning, reasoning capability is almost free for anyone to grab. But the interesting thing is that underneath you need to have a really robust policy, RL policy, that can actually achieve those plans in a very in any physically plausible way. So here we ask the agent to create a workspace. And so agent will look around, say, realize the relatively, so everything here is interactable, but the relevant object would be this monitor, and then the agent knows that in order to place the monitor, it has to face this particular direction, not facing the wall, and then moving the chair to create a space. And so this is an RL base, so everything's physically simulated. We also physically simulate the hand motion as well. So this is kind of give us here is another example. We ask the agent to continue to do, tidy up the room, put the shoes away, and then we ask the agent to do laundry. So agent can, so there's a long horizon, and then it's just really large space. So this is only in computer animation right now, character animation, but this kind of gives us a blueprint of what we want to achieve very soon with our G1, or not necessarily G1, just the humanoids. Okay, so how much time do I have? 10 minutes? Okay, good. All right, so we did a lot of this kind of a strategy, which we have some kind of a kinematic motion generators, and followed by an RL policy. But we also realized that the bottleneck right now is still this RL policy, because RL is still not that great in terms of in terms of being a very capable generalist, but it's really good to be a specialist. So one idea we are testing in parallel with this paradigm is to swap the position of RL and this generator. We usually use diffusion models. So the way we want to do it is we treat RL policy as a way to generate a lot of state action trajectory pairs, generate a lot of usable data, and then we will distill it using diffusion policy. And this is really pretty much like the original diffusion policy. What original diffusion policy proposed. So first you collect a data set of state action trajectories, and then you just use supervised learning to learn the diffusion model. And so can we apply this to a full body character animation, or just whole body manipulation? The answer is, for step one, yes, we have a lot of data already, but the problem right now is we don't have actions. But we also know that we can use RL to generate it, to turn, to cross that state to action gap, so we can get a nice state and action pairs. And the good thing about this is because RL is really just a data generator. I don't care how powerful RL is to generate all different kinds of data. If one sequence that failed to track, I just train another policy, right? Because all I want is just the data at the end. So I can train, if needed, I can train 2,000, 1 million policies to get the data set. Now, the step two is that with those data set, we can train a state condition diffusion model on actions. But when we try that, immediately it fails. And the reason is because that this numerical error that we were dealing with for high frequency tasks, like a lot of those manipulation, we see a lot of success with the diffusion policies because they're relatively low frequency. They're in relatively low frequency regime. If you're dealing with a local motion, this under actuated system, you have to balance. You have to have a high frequency control, and then a little bit of error is going to accumulate very quickly. So the one idea that we have for this project is called PDP, is to deal with the fact that data is too clean, and when you have a little bit of numeric error, you're going to be pushed off on the data distribution. So we need to make data a little bit noisier. And the question is that you have a state and action data. Do you add noise to state or to action, or both? And since I'm running out of time, I'm just going to show the results. Turn out that what we need to do, let me just play all this thing out. Okay, is to add noise in the state, but keep the action clean. And the way you do that is that you perturb the action at every single state. You perturb action a little bit. That will get you to another noisy state. But when you record the data as a training data set, you keep the correct action. How do you get the correct action? You get the correct action from your policy. So the key here is that policy you train at the very beginning, we thought that the purpose is really just for data generation. But now we realize that that policy actually has another utility, which is giving you correct behavior and around the noisy data, around the reference trajectory. And that is something that would be really nice to have, because otherwise you could have the data, collect data in state action pair any other ways. But if you do it from RL policy, you get this added benefit there. Okay, so with that, we're able to train one single diffusion policy that distill thousands of RL policy into one single policy, and it was able to track very well this entire data set. Okay, so now we talk about just state to action gap, and I'm running out of time. So I'm just gonna jump right into ego vision gap. This is one thing that we tried very recently. I mean, we started out with navigation that's been, research that's been developed for decades. But one thing we realized about humanoids is that the navigation is in 3D, right? The humanoids could not just move around, but it can also look around in this 3D world to make a decision. So one thing that's really important to us is that we need to know what is the optimal way for humanoid to move to, and where should it look at in order to make a decision, a longer term decision. And this is really hard to program or hard coded. So we decided to learn this from human. We want to learn how human moves and where human looks. So given a goal and 2D image you perceive, where should you move and where should you look in the near future? Okay, so that's the problem setting. And we could get that kind of data from area glasses or any kind of those AR glasses. It gives you very good 60 head position, and you can train a model that's conditioned on the egocentric observation in the history. And so this is what we did, and this is the prediction of, given what you just perceive in the last half a second, where should you be, where your head is going to be, and where the head is oriented. So basically 60 head position, that's what we propose. And I actually learned a lot of really interesting behavior. So for example, if the model perceives a small group of people right in front of you, it learns to wait. And if the model perceives intersection, like a traffic intersection in front of it, it learns to look to the left. And of course, if you collect data from UK, you will learn a different way. So this is kind of behavior so hard to hard code, right? And we can just get it from data. And we want our robot to be able to do that too. So in this simple case, we take the first frame robot perceives, the RGB, and we pick one pixel on that image and ask the robot to go to that pixel in the real world, right? So robot basically use that model, knows that where my head needs to be, where I need to continue to look. And then when we get there, we want the robot to touch it. Yeah. So eventually we want this to be, of course, manipulating, pick it up, do interesting thing. But this project is mostly just on the navigation. Okay, so I'm gonna skip that and jump to the final centurial gap. So luckily, Kaiser has talked most of it, so I can just skip most of the slides or the videos I prepared. But I do want to make one point here. So when we think about centurial, most people think about domain randomization, right? If you're coming from RL background, or domain adaptation. This is like a slightly more advanced version. But I actually want to go back to this very, very basic approach, which is just build a better digital twins with a better system identification practice. And the best way to do that is to build your own robots, because there's no other way you can system ID a black box like G1. And we actually did. So this robot is exactly the one that Kaiser showed you, but that's a separate project just to the design and development of the control itself. So it's a very capable robot, has a lot of degrees of freedom. It's definitely enough for you to do full body manipulation, both locomotion and manipulation. And you can see that this is a diffusion policy, this is the RL policy, and these are kind of like the MPC or more conventional control. And because the taller bot has a very strong upper body comparing to its overall weight, so we can do a lot of interesting things. And the whole thing is 3D printed with commercially available motors. And the reason we want to do in the open source, of course, open hardware project, of course. And the reason we want to do that is because we are so hindered when we want to do research on humanoids by those commercial robots. That there's just a big black box that we don't have this full ownership, like full stack ownership. That's what we want. And with that, we're able to, if you build your own robots, you can also build your own testing rig. This is also 3D printed, so everybody can do this as well. You take every single commercially available robot that's still a black box, but you could do a lot with it. You can do a lot of tests on that, and then we have this procedure that after you go through the text, the output of that is a whole bunch of parameters you directly type into your Mujoko simulators. And that way you can you just start at a better position to develop your policy and control. Okay, so with that, I'm going to just jump to this is the final project that Kaija already showed. So I'm gonna just jump to my takeaways and conclude my talk. Retargeting matters. A lot of people just do the simplest possible thing, which is a shame because you already know that you know if the kinematic part of the motion already look bad. You could fix with RL. I definitely agree, and we saw that as well. RL can fix so many things, but you never know what price you pay for that because you keep adding your reward terms here and there until it works. And you might be paying by a very suboptimal way to do something that could be done a lot easier. Exploit privileged information as long as it can be distilled, right? During RL training, it's always fine to use as much privileged information as you could as a teacher policy, because that can really get you to a very optimal position faster. Specialization before generalization. So many years with RL, I kind of conceded that RL generalism is so hard, but we can actually train many RL that's specialized, and then we distill them later. Where you look is just as important as where you go, especially where we have this new generation of a platform to play with. It's no longer just navigation is no longer just a 2D planning problem. If you are serious about system identification, build your own robot. But this is not for the faint. I realize that not everybody will want to do that. So that's why I think this kind of open source, open hardware project is especially important for our community. So with that, I'd like to thank everyone, and if you have time, I'll take questions.
Thank you, Karen. We have 2 minutes for questions. Anyone want to ask?
Hi, thanks for the great talk. I wonder if you have thoughts on at what level of abstraction we should learn from the human motions. With retargeting, we're tracking all the joint trajectories, but you could also imagine higher level targets, like just tracking the center of mass or just the direction.
Yeah. I just gave a talk at the dexterous hands, and exactly like what can we learn from the human hands. I don't know the answers for sure, and we're kind of trying different things. I think eventually what I would love to have is a low-level policy or low-level controller that handle the balance, handle the all those required detailed control of your joints and contacts and everything, almost like a black box, and nobody need to worry. And then the interface to that policy would be where you need to be, where your eyes and hands need to be. That I think would be convenient to a lot of people who only want to stay in the high level.
Can I ask a question about specialization before generalization? It's a really interesting concept. I mean, we see the similar thing from Sergey's talk. So it's interesting. I mean, the generating data, RL, is a very powerful concept. But RL always have that the cost function is a conditioned. How would, do you think we can, using that cost function, some sort of language to connect those like the semantic level to the action. Like, so if you have a bunch of RL data,
Right.
but each RL has a different cost function.
Right.
And if you can somehow connect that with the language to generalize those actions eventually, like how do you think about the connection to the cost function? Because the RL is always problem with the cost function.
Right.
And if you have a bunch of different cost function, but the languages, they're separate from the cost function, right? And then if you collect bunch of RL with those cost function, is there any way to connect back to the language?
Yeah, so let me see if I fully understand. So cost function only matters during training, right? So, but you're also talking about, so there's two ways to interpret your question. Are you saying that we use language to determine what cost function to use during training? Or you mean that once we're trained with a whole bunch of policies, with each of them with its own cost function, so basically they're different policy, and then we have a language that can decide which policy to use during inference time?
So what I'm concerned is like A cost function for A action success, great. That data, if you don't know the cost, that data can hurt other
I see. Yeah.
You have to go back to that high level language space so that you can condition each.
Yeah, for sure. Yeah. So I think there that not graphics people, but graphics plus RL community have come up with a whole different ways of commanding a fleet of RL policies during inference time, right? So you can do like mixture of expert. You have a different way to chain the policy together based on the language. So which all hinges on another layer of a model that knows how to route these policies. So given this language and the current observation, it knows that. And then when I say routing, it doesn't need to be like switching between them like binary wise. They figure out the weighting to actually use which policy by how much every single time step. Yeah, so there's ways to do that. I don't know if that answered the question. Yeah. Okay.
Thank you for the talk. It's actually a very great talk, and I'm very interested in this work because every single gap you mentioned is what gives me up at night.
Oh, really?
But
okay.
First is it seems like your talking pipeline still sort of rely on premises that the robot has a similar authority to a human one. But as you can see right now, a lot of the human robots, their design, especially their joint arrangement, is not exactly the same. For example, some robot will have the first joint pointing up.
Yeah.
Like this, not sideways. How would you modify or adjust your talking pipeline? The second question is the whole body control demo to show where the robot can actually go cyclic to move to shove a box away. That's really amazing. I just wonder like how much data is necessary, if at all, to achieve that kind of robot control status.
Okay, thank you. So the first question is the morphology. Yeah, so I think, yeah, retargeting is always a problem. The first rule of thumb is don't retarget in the joint space, right? Because a lot of things that we want to the very first thing is that what do you want to preserve? Like given a human motion, what is the important thing to preserve? I think that is something that had to be answered.
Sorry about that. What else is part of like some position?
Right. Right. So maybe the important thing is the path that you travel. Maybe the important thing is the distance you travel. Maybe the important thing is where your hands are. It has to be these two contacts on this particular object, right? So identify the invariance that you care about, and then backtrack from that, right? So, for example, and then actually 90% of them is in the Cartesian space. Right, so I think that just define. You don't necessarily need to achieve these constraints in this particular way human does, but you have to identify that. All right. So I think that just retargeting still there is no very standard fixed rules that will works for all scenarios. But I think always start off on the constraints, set of constraints you care about. Right? And if it's a dancing motion, then I think joint angle might be the good way to retarget. The second question you have is, sorry, how much data? Yeah, so first I want to clarify that that demo you saw is teleoperating. Yeah, so if your question is about how much data you need to get a teleoperating system so flexible like that, I think the answer is actually not as much as you believe. And that's why I feel like starting from human 3D human mocap data might be a good place, because it's a lot. I think we have more data than we can absorb right now. And to be specific, I hope my students there, but they're not. But I think it's a subset of AMAS data they curated. Yeah.
Thank you, everyone, and sorry for the delay. We'll now enter our coffee break session and also the poster presentation. Thank you again, Karen. Very nice talk.
Thanks very much.